Good morning, everybody, and welcome to the FPGA Programming Workshop organized by CASTIEL, the coordination action of EuroCC project. And thank you all for joining us. And I'm Martina Di Renzo from Cineca, the leading partner of EuroCC Italy. And I'm a project manager in the HPC department of Cineca. And today I'm going to manage the event. And I move on to the agenda for today. So we will start with the first speech by Xavier Martorell, which gave us like an introduction to FPGA. Then we will move on to Daniel with a presentation about FPGA shell and design flow. And we will leave a 5 minutes break between the second and the final presentation. And then the final presentation will be once again up to Xavier Martorell, who will be a presentation about OMPCC at FPGA, which is an extension of the OMPCC programming model to support offloading tasks to FPGA devices with an adding demonstration. And as for the previous events organized by CASTIEL, I will show you a short video presenting an overview of EuroCC and CASTIEL activities. So let's start.
Ranging from the areas of health and food security to energy and the environment, we are facing more and more societal but also technological challenges. High-performance computing, or HPC, in combination with HPDA and AI, provides the means to tackle not only these large, complex problems, but also to widen further use and uptake of iterative modeling and simulation technologies in academia, public administration, and industry by processing massive data and performing complex calculations at high speed. But what is the value of such a toolset without the competence to utilize it best? Thus, the European High-Performance Computing Joint Undertaking addresses this field by implementing the EuroCC project as part of their funding activities. Within the EuroCC project, National Competence Centers, or NCCs, are created over a period of 2 years in 33 participating countries. These NCCs are intended to serve as a single point of contact in each European country, bringing together the national stakeholders and thus boosting the use of HPC and associated technologies. To maximally utilize synergies between all participating countries and national competence centers, the coordination and support action, CASTIEL, is in place and active on a cross-national European level. By providing access to the excellent toolsets and enhancing European competitiveness as a whole, we can better face the challenges of our time. Visit us at www.eurocc-access.eu.
Okay, so thanks for your attention. I stop to share my screen, and finally we can start with the first speech and the introduction by Xavier.
See now the presentation.
Yes, we can see very well.
I have here the chat. Is that a black box for you or no? I guess you don't see any black box, right?
No.
Okay, perfect. Because this way I can see the chat.
Okay, okay.
So in the chat, actually, there is a questions in the end in chat or orally. I didn't understand that, orally. So feel free to interrupt me, and I guess I can speak for Daniel also. Feel free to interrupt us if you have any questions, even orally if you want. I think it's more productive. And then there is another question that says, will there be a chance to work on practical exercises on the FPGA hardware during this workshop? Unfortunately, no. This is the first workshop we do on FPGAs, I understand.
Yes,
and,
yes.
And the plan is to show things. On my particular option, let's say, or my particular personally, let's say. I have a lack of understanding of the FPGAs at the very low level. So I will show mostly top level things. Let's say from the OS and at the top. Daniel has some more insights on the FPGAs, and at some point we can plan for a second workshop that has some exercises, I guess. But this is tricky because accessing FPGA hardware is actually tricky. So needs to be planned, plan ahead. Okay. Yeah, and this is the answer that I gave. Perfect. So good morning, everybody, and thanks for being here. We will share the presentation with Daniel Jimenez Mazur. We both are affiliated with BSC, Barcelona Supercomputing Center, where we do several projects related to FPGAs. And personally, so this is Xavier Martorell. Xavier Martorell is also affiliated with UPC. I'm a professor at UPC. Okay. And actually, we have been participating. I have been participating, and Daniel also on some of them, on these past and present projects. Currently, I'm participating in Textarossa and MIP, and probably Daniel will comment also on other projects he's participating. And actually, we share the MIP project where we do the developments of RISC-V and FPGA. Okay, so this is the outline that I will follow for this first introduction. So this is like half an hour introducing the FPGAs. And I will start from very high level and going down. So yeah, let's start here. FPGAs are like GPUs, boards that you can connect to the PCI Express bus of a computer. And currently we have experience with, well, we have experience with x86 ARM, and here at BSC we actually have some experience, not personally, with PowerPC also. So this is the left side, discrete FPGA that you plug in onto your computer. And then we have a second option, which is also well known, which is the integrated FPGAs, smaller boards that are not thought to be plugged into a computer, but they can work standalone. So one of the main differences between these two things is that this one is usually just an FPGA. This one, the integrated system, is usually an FPGA containing a few cores, okay? And one particularly used type of cores is ARM. So in this particular chip, let me activate the pointer. In this particular chip that you see here, we have 4 ARM cores and 1 FPGA, okay? Usually these FPGAs have a smaller area than these ones, okay? Because they are mostly embedded. But you can program the same type of things. So a little bit types of or models that we have. So we have AMD and Intel. Currently, AMD bought Xilinx and Intel long time ago bought Altera. And here I'm naming a few samples of FPGA that you can connect through PCI Express. The Versal, Alveo, VCU 128. I would say Versal is the latest development from Xilinx, currently AMD. So I don't have experience on the boards. I have experience on the Alveos, and the demo I will show is actually on an Alveo board. Regarding Intel, the latest generation is the Agilex, and I don't have experience on those new models. I have experience on Stratix and Avria, okay? And also some experience with programming environments that both AMD, Xilinx, and Intel Altera offer. On the right side, we have the integrated. Also, AMD, Xilinx develop a few set of FPGAs, and probably a lot of them are missing here, okay? I'm familiar with the Zing 7000, which is 32-bit ARM. So these cores here are ARM cores 32-bit. and the Zinc UltraScale Plus, which is actually this one. This board actually is the one that we, in fact, the Seco company from Italy developed in the context of the Axiom project. That was probably near 2016. And then Intel Altera has also some integrated boards, and the names are like Cyclone and Max, and I don't have experience on those. Okay, so we get down a little bit and we see what's inside of the FPGA. So inside of the board, in fact, so if this is the board, we have the FPGA, which is this chip here, the XU200 or the XU250. Those are the chips that go to the Alveo board. And then we have some connectivity that we know about, the PCI Express, which is actually this connection here, and the QSFP, which is an Ethernet-like connection, which are these two things here. By the way, Daniel, if I say something wrong, let me know. Then these boards have internally a set of memories. Here we have some DDR memory. Others may have HBM memory. The 280 actually has also 8 gigabytes of HBM memory mounted on top of the FPGA. So I would say this is the set of interesting devices for us. Although we need to deal with the clocks. We actually don't use much the flash memory, which is for starting the initial programming of the FPGA when the machine does a cold boot. They may have some other things for maintenance, for debug, as a serial line when we use RISC-V, and these kind of things. Okay. So this is actually the second type of boards that that we have actually here at BSc, the 280, which in addition of the previous devices, it has also this 8 gigabytes of HBM. Both the DDR and the HBM, it's plain RAM memory. It's very similar to the global memory that we have in a GPU. Okay, so for you to have a comparison to do. So if you think that a GPU has a global memory on board, the FPGAs also have some global memory on board. Even that the FPGA chip itself may have another type of RAM, what we call the block RAM, which is probably similar to the shared memory that we have in GPUs. Okay, for this type of big FPGAs, and now I'm talking about the Alveo boards, we also have the FPGA splitted in some dynamic regions. Okay. And this is kind of regions that the vendor, so the chip producer generates, probably in order to organize internally a little bit the components of the FPGA. They can be bigger or smaller, and they can be like dedicated to some resources that are planned from the vendor, or they can be just free for the user to program. Okay. Let me see if I have any. No, there are no questions. Okay. So here you see actually the chip and the connectivity that I was showing before. As you can see here, for instance, if you have 4 modules of DDR, actually that was shown here. The 200 has 4 modules of DDR. The 280 has only 2 modules. So we went from 4 to 2, but here we have the HBM. And here, each one of the modules is actually connected to one of the dynamic regions, which means that any hardware configured in this SLR1 dynamic region has preference to access or has easy access to the DDR2, except that, of course, the hardware can be configured so that it can actually access any of the other memories, or of the other memory regions, let's say. Okay, then we have the QSFP, which is Ethernet-like. We have the PCI Express that I don't see it represented in the figure. And we can have a USB connection, for instance, as a serial line or JTAG. Yeah, and the connectors of this PCI Express and memories are attached to one of the SLRs. So this is another example. In the 280, we have the DDR and the HVM. The HVM is actually attached to the SLR0, okay? And then SLR0 and 1 have direct access to DDR. But as I was saying, if you program the hardware, so if you let the tools of Xilinx configure the FPGA given an algorithm, that those tools are able to access the memory from SLR2 also, putting the proper connections and the proper memory controls. Okay. Another example, which is the embedded, is the one that I was commenting from Axiom. This is actually pretty similar to the Xilinx, I think it's 102 development board for Zynq UltraScale Plus. As it has a Zynq UltraScale Plus, the name Zynq refers to the fact that it has cores. Okay, in this particular instance, we have 4 ARM Cortex A53 cores and a Virtex FPGA. It's a Virtex UltraScale Plus, Virtex 7 UltraScale Plus. We have, as we have the cores here, we need some memory that those cores can actually work. Okay, so those cores can actually boot Linux, and Linux will use this memory here, which is the host. But I label that as host RAM, because it is equivalent to the memory that we will have in the x86 PC if we talk about PCI Express based FPGAs. And then we have a small set of memory here, which is, I think that those were half a gigabyte, that will be equivalent to the global memory I was talking about. Okay, but in any case, in this particular embedded implementations, we have actually experimented using applications on the host RAM running Linux, and then transferring memory, so transferring data from the host memory to the FPGA and vice versa. Okay, and we have experimented more this particular option rather than using the local memory, the global memory in the board. Additionally, when you have one of these small boards, you have a lot of connectivity. So you have gigabit Ethernet, regular standard RJ45 connection. You have a micro SD from where you can actually have Ubuntu installed and a Linux kernel. You can have some Arduino or other types of connectivities, the power, USBs. In this case, we had USB 3, I think, USB-C connectors that we were actually using in Axiom to implement networking between boards. Then we have some boot controls, the UART for debugging, a mini display port in order to trigger a display, and other types of connections. These were actually USB 3 connections. Okay. Okay, let me see if. Yeah, there have been some questions, but Daniel, thanks, you have answered. Okay, so just to compare two GPUs, no, what I was commenting before. So my understanding of a system with GPUs is you have a host and the system memory, and then you have the board. That would be the board that you plug in the system through PCI Express. You have some global memory, the device memory, and you have some multiprocessors inside of the GPU chip. No, the GPU chip has the multiprocessors where you have the CUDA kernels or OpenCL kernels running. Okay, so if you replace the GPU by an FPGA, you actually have the FPGA board with some device memory and this reconfigurable logic that I have also split it like we have the SLRs, that you can actually, or to let the vendor tools to program that. Okay, and my impression is that we can establish an equivalence between the shared memory in the GPUs, which is something that is internal to the GPU, with the block RAMs that we have in the FPGA. So usually what you do is you copy the data from the device memory to the block RAM, and then you let the logic to operate on block RAM and put the results back on the device memory and potentially to the host if you want to check that the results are good, or you want to display them in some output device. Okay, this is the way we usually do. Now we are going inside the FPGA, the particular chip, and we see here the set of interfaces and the super logical regions, and a little bit the pattern that we have in each one of these regions, okay, which are the configurable logic blocks, which are the low-level components that we have inside of the FPGA, that are the ones that the vendor tools reconfigure in order to implement your algorithm. Okay. So actually here, for each one of these small squares, we have the configurable logic blocks. We can have also DSPs, which are devoted to mathematical functions. We can have block RAMs, so portions of memory that is addressable from other of the configurable logic blocks or from the DSPs. And you also have the interconnect, which is probably represented by this set of lines. No, you have kind of an interconnect that needs to be also configured in order to move data from one component to the other. And you see here the 3 SLRs in this particular example. Okay. So if we go inside a configurable logic block, we see that they have a few components, and I have taken this information from Xilinx. So I guess that Intel Altera FPGAs are similar. For instance, I know that regarding DSPs, Intel Altera FPGAs they have much bigger DSPs than Xilinx. At least if you compare Stratix with Alveo, which is not the latest generations, but the ones that are actually used, or at least the ones that we use here at BSc. So we have carry chain that is used in order to implement adders, counters, comparators. We have multiplexers, 8 or 16 to 1. We have shift registers. We have some small memory, flip-flops. We have lookup tables that you can program. Well, the vendor tools will program with your functions. It's a 6-input lookup table, and I think it has 1 or 2 outputs. So 6-bit input gives you 64 entries in the table. So you access the entry. I think it can have 1 or 2 bits, and you get the result. And then you have distributed RAM, which is something inside of the configurable logic block that is recommended for very small values, 1 to 128 bits of data. So I would say if you have a double precision number, you will use this distributed RAM in order to propagate the value between configurable logic blocks. Another big block can be a block RAM that I understand is a particular implementation of a RAM. I think it's like 36K bits per block or something like this. And it is also configured appropriately by the vendor tools. And you can also have DSPs. Okay. So looking a little bit in detail on some of these components. As I was saying, I took this information from AMD Xilinx. Lookup tables. This is actually the implementation of a lookup table with a few entries and a few outputs. Actually, these are the 2 outputs for getting 128 bits of data total, and then you select the information that you want to get. Regarding how many of those we have, in the zinc ultrascale that we are using in Axiom, we have this number, 274,000 of these components. And this is a number that gives you an idea of the number of resources that you have. But as we are not actually programming the FPGA in the low level, we use these resources from C++, and the vendor tools use a number of them. Okay. Of course, if the vendor tools are not able to implement your algorithm in less than this number of lookup tables for the particular algorithm that you are trying to put in the FPGA, the resulting synthesis will not work, will not fit actually. And the tools will say, I cannot generate the final bit stream for that particular algorithm. As you can see, in the Alveo U200 and U250, we have particularly a bigger number of lookup tables. Okay, and here I'm representing per logical region. Okay, so it's even single logical region is also sorry, is already more than one zinc ultrascale plus. Another example, the flip-flop. Okay, it can also be used as a latch. So we have 16 flip-flops on a CLB and a total of 500,000 in a zinc ultrascale and a few millions in the U200 overall. It's just a 1-bit memory and can take the output from a LUT. So it can take an output coming from outside of the CLB on from the actual LUT A that is already there in the CLB. Okay, actually we have I think it's 8 of these flip-flop latches connected to the LUTs in the same component. Okay. And actually, I don't have the details on how the vendor tools map the things onto these components, but this is something that is implemented on their tools. Okay. Then we have the block RAMs. Okay, so they are dual ported 36, I think it's K bits. They can also be seen as a programmable FIFO, first in, first out, so it's like a pipe. And they can be configured with different configurations, like 32 K bit. So yeah, this is 32 K bit, or 4 K bit by 8 bits, which means 4 K bytes. No, for this would be 4 K bytes, and it can reach up to 1 K bit of 36, which means something like big numbers. No, 32-bit numbers. You have 1 K. So here we have the numbers, also much bigger on the Alveos than the zinc ultrascale. I have to say, now that I remember, that here I'm looking at a particular size of the zinc ultrascale plus. But if you look at the manual, you have a lot of different sizes of the zinc ultrascale plus. This is an intermediate size, I would say. Okay. And then the advice that we are given by the vendor is, please use as many blocks as possible to achieve data parallelism. So don't try to put all your data in a single block RAM, but use different block RAMs so that you can get parallelism while loading and doing the operations on this data. And this is the particular implementation of, well, the particular view, high-level view of the block RAM component. And then we have the DSPs, which are actually very interesting because they actually do the computations. No, so this is also fitting in the. I understand they all fit in the space of a CLB. So here you can have several signals like A, B, C, and D, and do a kind of addition, multiplication, and some additional logic or addition and subtraction. Okay, so overall, you can multiply, you can accumulate, you can do the just pre-adder. You can, let's say, split the bits in 24-bit quantities or 12-bit quantities, and then they act as SIMD unit. And my impression is that this should be a 4 by 12 or 2 by 24 or 48-bit. Okay, sorry, but this is probably a 4. Then we have logical units and or sure, all kinds of things, and they also have a pattern detector. So they can have a pattern detector. I think it compares, yeah, it compares the input C that comes here compared to the multiplication of A by B. So you get A by B, you multiply, and then this is the pattern detection, and it says, yes, the pattern is the same or not. The pattern is different. Okay. And this is a sample design that I was just taking the photo from Xilinx, okay? So it's a sample design that contains memory access. They call it memory interface generator, which is this thing here. Then this memory interface generator drives the DDR memory and is able to be connected through the AXI4 slave. This is a typical connection that I think all types of FPGAs use, this AXI. Connects the interface generator to access the memory controller, let's say, to access the memory with the user logic that is implemented in the blue thing, okay? This would be probably an FPGA with 2 SLRs, and this is the way the things get distributed in this particular implementation. Actually, the vendor tools allows you to open the block design and also the synthesis design, and you can see this kind of low-level details. But you need to actually be familiar with the details of the FPGA in order to probably understand the last bit here, okay? So an initial set of comments about how to program the FPGAs. So we have high-level C++ programming. From my perspective, this is the more productive or more easy way of using FPGAs. Actually, as far as I know, no Fortran support from vendors. There may be some other producers' tools supporting Fortran, but I guess it's not very stable, let's say. And what the vendor tools do is to transform the C++ onto Verilog or VHDL. I think they do both, and then they use one of them to actually synthesize for the FPGA. Okay. Of course, you can also program the FPGAs using Verilog and VHDL. There are many different types. There is also System C, a lot of different languages that you can use to target the FPGAs. And this is the part that I lack. So I am not familiar with Verilog or VHDL, so I cannot go deep inside on this side. I have colleagues that know about it. So if at some point it is interesting, we can think of a low-level description in this way. So from there, you get a set of design source files where you can do behavioral simulation. All vendors provide a set of tools that also do simulation before doing the synthesis, because doing the synthesis takes a lot of time, like a pair of hours, maybe just 45 minutes, but it's some time that you need to spend to get the final reconfiguration for the FPGA. Okay, so sometimes it's good to do behavioral simulation and you see if the behavior that you are expecting is good. Then when you have these source files in Verilog VHDL, you do the design synthesis that goes from HDL to gates and generates something that is low level, what they call FPGA netlists. And there you can do functional verification. There are tools to do that. And then the design goes to the implementation and place en route. This is doing this static time. You can do there the static timing analysis, so you know how much time it will take every component because it's already synthesized. And finally, there is the step of bitstream generation that allows you to load that bitstream onto the FPGA, which implicitly reconfigures the FPGA, and then you can run your algorithm there. So the vendor tools for AMD provide are named Vivado HLS, BTS HLS. This is the C++ support. Vivado and BTS. BTS is the new implementation of the tools, which is using newer compiler based on LLVM. They have graphical and batch tools in order to either see the program in an IDE and then synthesize, or just give a set of commands and synthesize for the FPGA. And the input code that usually AMD Xilinx take is C++ and OpenCL. So they also have an OpenCL implementation, so they are able to compile OpenCL kernels expressed in OpenCL. I'm not sure about the version. Actually, I'm not sure if they support OpenCL 2 already or not. I know that they were supporting OpenCL 1.2, I think. And then in the Intel Altera side, we have also the equivalent to Vivado is Quartus. Quartus Prime design software is the one that actually knows about generating from VHDL or Verilog. Also graphical and batch tools. They compile C++ code and OpenCL kernels. And here they have this particular addition that I think is very interesting, although it's still a little bit low level, which is taking the C++ lambda functions in order to do the synthesis of the kernels. And this is what they call one API. One API is actually very big, and probably it has much more than what I have just said. But it is definitively based on encapsulating functions as kernels for the FPGA. These are originated from CodePlay and Khronos, the SYCL approach, and they do these lambda functions encapsulated in C++, although they can also encapsulate plain C++ functions for the FPGA. And just a brief introduction on and maybe a good refinement of the overall system that we use here at BSc. So we have Intel boxes and ARM boxes, okay, running Linux, okay, and then on top we run the application. The application is linked with our runtime system, Nanos++, and also the support libraries that we have here, Xtasks, that should be XDMA. And then these particular libraries talk to the QDMA driver that Xilinx offers for Linux. In fact, and this is also a different wall. So it's a full wall of drivers. Actually, Xilinx offers 3 different drivers: QDMA, XDMA, and the OpenCL driver. And you need to be aware of what you want to do in order to get the proper driver to use the FPGA. We decided to go for QDMA because we thought it was the one that was actually promoted by Xilinx. This was probably, I would say, 4 or 5 years ago. And now we have realized that actually both QDMA and XDMA, Xilinx DMA, are incorporated in the OpenCL driver, but we actually don't know how to use them. So if you want to use OpenCL, just install the default drivers to support OpenCL. If you want to use something more generic, I would suggest to come to OMSAT FPGA and use QDMA. From the QDMA driver, we trigger a number of queues, and we have actually a hardware runtime managing the tasks to be executed inside of the FPGA. Okay, and I think this is mostly of my first part. Okay, I have some references here for your reference, okay, including those on FPGA. And now, I don't know, maybe we can open a small set of questions.
What API? Xavier, at first, thank you so much for your presentation. And
You're
yes,
welcome.
if anyone would like to put their question on the chat.
So I see one question here. It's one API should probably be data parallel C++. Yes, this is correct. But I think Intel names that as one API. At least that's my understanding. Data parallel C++ is the particular compiler that Intel offers. Yeah, DP C++ actually. Agreed. What OpenCL provides compared to QDMA or XDMA drivers? As I understand, the OpenCL infrastructure that they have here. So if you put here the OpenCL driver. So if you put here the OpenCL driver, actually what you have is both functionalities, XDMA and QDMA. But actually what AMD Xilinx promote is to use OpenCL kernels. And with OpenCL kernels, you have some inputs, the kernel, and some outputs, and nothing else. So we cannot implement actually the hardware runtime, the queues, our particular implementation of the instances of the accelerators. So from my perspective, it's too limited. But I may be biased. Okay, so Nanos is when I will explain ohms at FPGA. So I will also explain that Nanos is our runtime system. And how, let me see that I don't miss any question. And how quickly does the program to get written to the FPGA? It depends on the program. I will show you a few examples, basically very simple, matrix multiplication, okay, where you will see how we actually write programs. But this is in the third part of the workshop. DSPs work both on integers and small floats. Small floats because I think they have a reduced mantissa of 25 bits. So if you want double precision, you need to concatenate a few DSPs to do that. And the vendor tools does that automatically for you. Even if you program in VHDL, I understand. Okay. So that was the last question. So I'm happy to switch to Daniel if